Okay, so you all happy about the exam being postponed? Yes, I mean, it was funny, a posse came in yesterday afternoon, and they looked like they were serious. It looked scary. And, and the thing is that we're all in crisis as well. I mean, we're all trying to get ready for this controlled conference deadline on Friday, and me as well, so I haven't been sleeping either. So I'm very happy to postpone it. So, you know, everything's the same, except I've got a surprise for you, which I'll announce in a half an hour. So yeah, this week's same time next week, same things you have to study, except stay tuned. So last time we had this, believe it or not, beautiful common filter, and it says recall common filter in very faded letters, because none of you recall this after spring break. But you have this very, very general state space model, which, you know, is a reasonable fit for a lot of control systems and communication and signal processing. And then we have this filter. And it has a pretty form, because basically you have the state evolution, looks just like the state evolution here for the estimates. But you replace the noise with a sort of like you call an estimate of the noise. You know, this is the innovations, so it's going to be, you know, an uncorrelated sequence, and then you've got some gain here. So this whole thing is, again, it's like an estimate of the noise, and you have some completely non-intuitive junk here. This is the hard part. I mean, again, the reason there's so many typos in Bruce Heick's notes is it's so boring to go through the step by step. You know, the main conceptual concept is the innovations, and that's really pretty. But then you can see I got bored writing this down. I just gave up. All right. So one thing I forgot to mention last time. So, you know, it was really good that Caleb said, well, hey, could you go on a bit more? What are the applications? And I mentioned weather forecasting. Of course, in any control application, it's really typical that you have measurements. You don't have full states of measurements. You have limited sensors. But there's like the typical thing people give as an example is least squares estimation. And why? I just forgot to do that. So So it's just it's really useful to give this example, because it's like this shows how you can apply these techniques in places you wouldn't expect to. Okay, so basically, if you've taken a control course, you've looked at autoaggressive models maybe or something, and this could be an input-output system. So this vector, this phi k, typically it's a big vector with past y's. And past inputs as well, there's inputs to the system, but it's known, all right? And we have these measurements, and typically assume this noise is white. If it's not, you'll have to modify phi. You'll actually have to enlarge the regression vector or do some other things. And the question is, you'd like to estimate this unknown parameter theta. And it's obvious that this is a special case of that. If it's obvious to you, tell me what f is. Oh. Yeah, but not 1, because F's the matrix. So F's the identity matrix. So basically, you can look at these. I just flipped things around here. I don't know why I did that. Maybe just to confuse you. But you've got a HK here, which we thought of as a deterministic sequence. But as long as it's known, we can sort of pretend it's deterministic. That's sort of true. I mean, if we don't know the future, there's some issues. But if Phi k is totally known, and we've got a bunch of data, we could just treat it as deterministic. If you've seen this before, here's a typical estimate. So I'm not going to give you any justification. I'm just going to, blast away at this for fun. So what you do is you say, well, the assumptions on the noise here, again, are the same as here. So Vk is an uncorrelated sequence, and you typically assume it's independent of Vk, but all we need is uncorrelated. And what you do is you think, if it's uncorrelated, I can multiply both sides by Vk, and I'll have phi k dot vk, if I average that, that's small. Yeah, no, maybe I'll do it. So I'm going to multiply both sides by phi k, but I've written this in a really unfortunate way. I put theta before phi, but we know I can flip that around. Right? And then 2 is to sum. To do that. And now stare at this for a minute. I've got data on the left, which you can imagine sort of grows at rate n. In fact, divide both sides by n, just for the fun of it. I'm just for intuition. I'm putting that in green because I don't want you to keep that. I just want us to think for a second. Basically, you can assume that this product is an uncorrelated sequence, and you could assume that basic law of large numbers holds. So as n gets large, that's small. So this whole thing, like by CLT, it's like go to square root of n. Well, this thing here, I mean, if this is 0, you're dead, right? If phi k were 0 all the time, you can't know theta. So you assume phi k is big enough, so the average here is not going to 0, and then this is the data there, right? And so this is small. Anyway, you ignore it. And so the least squares estimate I'm going to put it down here. Hopefully you can all see it, because I want to keep it. You just invert that and multiply it to the other side. Oops. All right. Now, if Gauss were in this room, he'd kill me, because he'd say that's not right. I'm saying that I want a estimate, which minimizes some least squares criterion, and no, Professor Mine, or Dr. Mine, or Mr. Mine, you're full of shit. So the real derivation is not hacking away like this. There's a real least squares criterion you can look at, and I'm not going to derive that. So you can go and look in Wikipedia and read about that. I'm just saying this is a cheap way of deriving the formula for least squares. All right, just ignore the noise and invert. Now again, you can derive this using much more principled approaches, but But given the fact it looks like the common filter, we should be able to come up with a much better algorithm. And why is that? The common filter makes use of the variance information of the noise. That's not being used here. The common filter is initialized. The common filter, you're allowed to say, hey, I think it's somewhere around here. I basically can say, I believe that the state here is just a constant, right? I can say that I know that theta is in some big ball with high likelihood. So there's a lot of information that the common filter can make use of, while this least squares point of view doesn't. And it's good and bad. I mean, it may be that you really don't know anything, and so any kind of initial conditions here are just meaningless. But a lot of times you do have some insight. All right, so let's do it. Let's do it. So our model is xk plus 1 equals xk. Okay, so the noise was 0, so we called qk, the covariance of the noise is 0. And then we have our observations. And so again, I'm writing it now in the right way with phi k coming before the state, right? And we've got, and then we've got initial condition x0. I would just call it theta hat 0. It's just our initial guess for the parameter, and we have some sigma 0 as well. Questions or clear? No. Yeah. Oh no, because no, you missed something. Right here you have observations where, like, think of scalar as observations. Their observations are dot product between a state and this matrix H. And you see here the observations are dot product of a matrix. It's not called H anymore. It's called phi, and theta, which doesn't depend on time. But that's okay. We can have really boring state processes. Yeah. I should say though, it also, it's really cool. A lot of times you don't have these. You have these regression problems where theta slowly varies with time. And then you can apply the common filter for that as well. That happens a lot in applications where your parameter might be changing and you'd like to track it. Yeah. No. H is the observation matrix. Oh no, these are all just matrices. Yeah, so these guys are matrices, and these are uncorrelated sequences. Yeah, right? So this is a state space model. So there's no transfer functions at all. Yeah, and but in this case, with scalar observations, HK is just a column vector, and that's just a dot product. Yeah. All right. So you get the common filter then. The filter is given by right there. Oh, I'll get some. Now let's call it theta. Well, let's just call theta hat k equal to the estimate. So again, the filter. I've got the new estimate of the parameter is f times the old estimate. Well, f was the identity matrix, and then I've got this nonsense here. And so you've got your innovations there, like before, right? And the gain. Here's where I'm not going to do it. I thought about doing it, but it just takes too much time. You can write down the gain. You can see there it is. I'll begin this. Kk is equal to the identity times sigma k given k minus 1. I've got my phi k. I'm just writing down what I see here. And this whole thing is a scalar inverse, because, that's a scalar, RK is a scalar observations. So again, I'm not going to do it. Maybe I'll find, I couldn't find it online even, but this whole thing unravels. And what you end up getting is basically the same thing, but you end up getting an initial matrix here. You end up getting that theta hat k is actually, and again, I thought I'd be able to find it, and I couldn't find it, but I'll send this off to you in a note later. But it turns out to be just that with some modifications. It's it's something. I got to put a question mark here because I just discovered this morning that I didn't have it. So just the same thing. And I know there's some normalizations here, so I'm not going to tell you what m is right now. It has to do with the m is a function of this guy, of your initial covariance. Yeah, and I just wasn't able to get it in time before the lecture. Yep.
With the Kalman filter, is it heavily dependent on initialization, like performance? Some methods are really dependent on initialization.
Yeah. So the wonderful thing about the Kalman filter is that under some really mild conditions, and if you take a control course, you learn about them, it doesn't care about the initial condition at all. And those conditions in this case, to answer your question, well, actually, I'll come back. All right. Well, I'll answer your question. So basically what you get is theta hat n goes to theta as n goes to infinity if under just incredibly gentle conditions, like the Kalman filter conditions, so first of all, you're going to need bounded noise, and then you need, let's say phi k bounded. We don't need that, but let's do it. And the minimum eigenvalue of the summation k equals 1 to n of phi k transpose goes to infinity. And that's called persistence of excitation, or weak persistence of excitation. This is so far outside of the course, but PE is persistence of excitation. So remember I was saying the amazing thing about the Kalman filter is you don't need to explore anything. You can learn things. You need to explore. You need enough signal to noise ratio so that you can learn the parameter. But yeah, in general here, there's a observability property that guarantees you get you forget the initial conditions. Yep. Okay, cool. So yeah, I apologize for this. I intended to give you the full story, and I thought I had the notes, and I can't find them. And I kept it online. I spent an hour online this morning, and nobody had it. I mean, it's just, but there's that. Yep, you had a question, or somebody did? Yeah. And by the way, you can see the beauty of this. I mean, this thing, the value of this. I mean, this thing isn't even invertible for a while, you know. And actually, when you do this, when you put in the right thing here, which is going to be that or its inverse. Like, I have to go double check. This is now invertible, inverse, same as that. This will be invertible for all n, so it's more stable. So it's better. What you get from the common filter is better than least squares, even if you don't know what these guys are. It's more robust. All right. So I blew that off. So I just wanted to give you one example. Anything happy? Yes.
Why did you say this is better than least squares?
Oh no, it's just this. No, it's only the comment I made about the numerical stability. That you're going to have to wait a while for this to be invertible, and then it might be very ill conditioned. Well, this is going to be, you know, perfectly reasonable to invert for all n. You know, and the thing is that this. Oh yeah, and I should also say, the implementation you get here is much better than this because it's recursive. You know. So you can make, so Gauss would have told me, Professor Mine, or Dr. Mine, or Mr. Mine, are you idiot? I would never do that, I'd make it recursive. So there's a recursive version of this, but it turns out to be just, you know, a version of the common filter. But this gives you the right initialization. Cool. Now I can kill it.
Mm-hmm. I've seen that before in like the ethanol or like literature.
Well, persistence excitation,
Is that more?
it comes up in other contexts, yeah. Well, it's a standard term in statistics. So, and then, yeah, it's only in these linear settings it's used. You know. But people might use it in other settings. You know, but that's the definition. You know, either that sum is infinity or its average is bounded from below. All right, cool. So, this is what you've all been waiting for. We're going to part 3 of the course. So, and I guess and this is, I mean, it has some really pretty concepts, and again, it's going to require 1 or 2 more flashcards. So what's a Markov chain? So I'm going to start out really general, and then I'll get down to something more concrete. All right, so we'll get to examples. I'll make this concrete. But I just want you to visualize a sequence. It's a stochastic process, and it takes values in a state space called X. It'll typically, like in a typical course, like undergraduate course, it'd be finite or maybe countable. But why be bound to that? It could be an Rn, or it could be in all sorts of things. So, and I use this X here. And so a great pair of authors in 1993 declared that if you say chain, it means discrete time and not discrete space. And those great authors were me and Richard Tweedy. So forget everybody who says that chain means it's a finite state space, they're wrong. The chain is discrete time. We've got to, somebody's got to fix language, and most people agree with us. Most people go along with a Markov chain is a discrete time stochastic process with certain properties. And what is the only property? So we need so we have a state space. Guess what else we need? We need probabilities. And so it's going to have like a sigma algebra associated with, No, it's not. I mean, it's a baby little probability space. It's not, though. I'm going to call it B. It might be the Borel sigma algebra on X if X is Rn or something like that. It's just that it's not. It's here. There's already a big probability space out there. I don't know what it is. There's a giant omega and little omegas and all that. But I want to be able to look at for any. So here's a defining property. So I go. It's a stochastic process taking values in state space X, which has an associated sigma algebra B, such that for any A, so any A in this sigma algebra, and any initial state, and any time, any pair of times, I have this very convenient property. If I want to predict where the Markov chain will be at time t1, that's equal to, and most of you have seen this, right? I actually cross that out. We don't need that. No?
What does it say at the bottom?
Where? The probability that, so for any target set, think about it. I've got, in the future I want to know, is my process in a set A? And I want to find the conditional probability of that event. See, that's an event. That's we're assuming that. Given the entire history of the process, you can guess, even if you haven't seen this before, can't you? No.
It's conditionally independent of all the others except the previous.
Yeah, how do you say it? Yeah. So he said it. You're right about something else. You're going to see, you'll see when you look at joint distributions, then you'll be able to repeat that answer. So how would you write that down?
Probability of x of t1 and a given, it is equal to probability of x of t1 and a given x0.
Yeah.
No?
All right.
It's like it's only dependent on the previous.
Yeah, so basically it's supposed to capture the idea of a state. So in the state space model, now this is not a Markov chain because I only assume that WK is uncorrelated. But if I wanted to look at, if I observed the process up to time k and wanted to predict where I'd be one step in the future and wanted to use like the best linear predictor, this is white. Remember, what's the best predictor of xk plus 1 given xk? And everything else. So if I, like, what's the wide sense conditional expectation, say? We were doing the best linear, the hat means the best linear estimator. What would it be? So remember, this is uncorrelated with everything in the past.
Is it G star?
What?
G.
No, look, it's this FK. Yeah. So I should have said at the beginning. So Markov chain is supposed to capture the notion of state. That given the current state, the past is irrelevant. The past is irrelevant. So the initial conditions are irrelevant.
That's what I said.
You said no. I thought you said X0.
Huh?
I thought you said
I said it based on those 2 times you provided.
no. No. So what was it? Maybe I misunderstood you. So basically, I don't need all this information.
Right.
I only need a subset, and it's only the most recent. Yeah, no, I heard you say X0. X0 is gone. Okay. So there's a formal definition, and then we can sort of get down to applications and all of that, and try to figure out what this means. Yeah.
Are both sides of that probability?
Oh no, T1. Oh, I see. See, that's why there's some confusion. 0 is equal to 1. Yeah. Maybe that's why. Yeah. Oh yeah. Oh come on. Somebody should have said that's easy. If it's up to T1, then it's what is it, by the way? What is it, everybody?
1.
No. What? Hey, this is a good exam question. What's the Oh no. I want to make sure you know this. What's the probability that x of T1 is an A? Say, given x of T1.
X of T1.
Yeah. Yes. All right. That satisfies your, I mean, that's it. It's known. I mean, we know this is supposed to be a function of x of T1, number 1, and it's supposed to be the minimum mean square estimator. Well, this has 0 mean square errors. Okay, so there's the Markov property. All right, and the tip that well, actually not a typical example. The only example. I mean, you can say this under really general conditions, that a Markov chain is just what I'm about to write. All right, so basically, I mean, really, this is, you can construct a model of this form for any Markov chain, basically. Maybe there's a counterexample out there, but anything that you ever look at, you can write in this form. There's a way of actually representing it in this way. And so basically, it's just like a state space model, but it's a nonlinear state space model. I'll get rid of this. Okay, cool. So, and that's, you can imagine it's an incredibly useful model for all sorts of reasons. You can imagine if you're looking at nonlinear filtering, having this model, you can see having this idea that the current state is sufficient to summarize the past, will be really useful in applications to estimation and all sorts of things. But there's one thing wrong, is that it's still a bit complex, because describing this thing is really complicated. Because to describe it, you would need this for every t naught and t1 and every a and every possible value of x of t naught. There's a complexity thing that goes out the window. So typically, we assume time homogeneity. Okay, so as you all know, because you all studied for this exam, this conditional probability is just a conditional expectation, and it is a function of this random variable, right? You know, so I'm just specifying what that function is. Cool. All right, so basically, you have this shift invariance property, that the probability of going from x to a in t1 minus t naught seconds only depends on the time distance. It doesn't depend on anything else. So it's like over here, it's like getting rid of the f, you know, and it's like making qk equal to q0, just making it fixed, you know. So just what we always do in like a control course. We just start with time invariance. Nobody puts in that k in a control course.